Hi everyone, thanks for joining our webinar today. We're really excited to share our insight into injection molding best practices and design tips with Xometry. First, I'd like to introduce myself. I'm Blair Stanton, Marketing Director at Xometry. I want to go over a few notes before we get started. We're going to have a 30-minute session going over injection molding with Greg and Travis, followed by a 30-minute Q&A. Feel free to submit questions during the webinar for our Q&A session at the end. And we're also going to be sending a webinar recording around for anyone who'd like a copy to share with your colleagues. Next, I want to introduce our team. First, meet Greg Paulsen, Director of Applications Engineering at Xometry. Greg brings many years of experience and leadership to our team here at Xometry. He was a project engineer for many years doing rapid prototyping, so he brings subject matter expertise as well as manufacturability expertise. He's also the star of our YouTube video series. Next, meet Travis Minyard, who's a newer face around here. Injection molding, he's an injection molding applications engineer at Xometry. Travis has 27 years of plastic molding experience. He has held positions in the industry as a mold designer, journeyman mold maker, tooling manager, tooling engineer, and cost engineer. He has worked for some of the largest injection molders in the United States and has worked in the automotive, medical, consumer, electronics, and military fields. So thank you again for tuning in, and with that, I'll pass it over to Greg and Travis.
Great. Hey, thank you so much, Blair. And we're really excited to talk about injection molding and how we've added it to the Xometry platform. For those of you who are not aware, we have a very streamlined experience for whatever you're looking to manufacture, whether it's CNC machining, sheet metal, plastic parts via 3D printing, metal parts via 3D printing, urethane casting. But one of the things we were noticing was that people who were ordering plastic parts frequently, we'd see the designs change, but we'd only see low volumes either going through casting or 3D printing, then kind of disappear. And we knew that there was an opportunity to scale up because with our other metal technologies, we could scale up to the thousands, but with plastic, we didn't really have a fit there. So we knew there was a big opportunity to add injection mold to our service. And what injection molding is it is a way to make a plastic part highly commoditized by having a upfront fixed tooling cost spread over thousands and thousands of parts to get a lower per part count. So what I want to talk about today is injection molding, how we're using it for low volume production manufacturing of plastic parts. And we're going to break this session down into the basics of injection molding. What is it? What makes it different from the other processes that we've offered at Xometry? I'm going to talk a little bit about the common mistakes when designing for injection molding. Travis is going to talk about how some of these things translate into cost drivers for injection molded parts and what you should look at both from a design standpoint as well as a practicality standpoint when you are looking at injection molding as an option. And we're going to talk more about how our injection molding quoting works at Xometry right now, and then finish off with some question and answers. And we're always happy to take some questions. As Blair said, on the GoToWebinar interface, there's a little questions tab. Feel free to present your questions there. We're going to be taking notes of those throughout the session here, and then we'll get to them at the Q&A session.
Thanks, Greg. This is Travis speaking. I'm going to sort of show you the basics of injection molding, sort of on our slide here. So injection molding is a new platform that Xometry offers. It's unlike 3D printing or machining or casting. It's a completely new process. So I'm going to explain the process here in a nutshell. So the injection molding process is a shape forming process which molten plastic is injected into a steel or alloy die that is shaped like your end product. Injection molding is mainly in the production of a solid object. And like Greg said, it is made to make thousands and thousands of parts. So if you look at the process itself, it's relatively simple. I know some of you people out there who probably have experience in the injection molding field, but like I said, this is just basic. So one, the material enters the barrel of the machine and begins to melt. The material looks like BB pellets, if I could explain that. And then two, the screw rotates inside the barrel. It moves the material towards the front of the barrel. Once the material is up front, the screw stops rotating and it serves as a plunger. And in the front of that screw, there's a check valve, and it closes off. The material is metered in the front, and then it's shot into the mold at a very high pressure. And I mean high pressure, anywhere from 2,500 to 22,000 pounds inch per inch, or inch PSI. And then 3, the mold is cooled. The part is cooled, the mold opens, and the part ejects. So just to talk about the mold a little bit, there are anywhere from 20 to hundreds of pieces inside of a mold. Okay, there's different actions inside of the mold that serve different things. So if you just look at the slide there, you have some of the stuff like the cooling channels, the parting line of the part, the sprue bushing, the ejector bar. There's lots of pieces to a mold. And then once it's molded, you get a runner. 4 runner and sprue are removed, leaving a final part. So that's injection molding in a nutshell. So here's a typical part. Greg actually found it.
I may have taken a stapler apart on my desk to get this photo.
So just to sort of break down, you know, we call this the ugly side of the part, right? So at the top picture, you have the gate. The gate is where the material flows to fill the part. You have the bosses in there. You have the ejector pin locations, the little subflush circles. Those push the part off of the mold. And then there's a lifter on the opposite side. So anything that moves inside of a mold, including lifters, slides, some people call them cams, anything that moves is like that slide says, these add money. Okay. And then you have the cosmetic side of the part, that we call it the pretty side of the part. You know, it's just aesthetics, right? It's ergonomics. It's those types of things.
And just something to note here. So this is a piece. This is actually a semi-flexible piece. It's a thermoplastic elastomer, TPE. And something you'll see on the gate here is the gate is a little bit protruded because it's been once it's molded, that piece is clipped off with usually a diagonal cutter manually, and then put into, you know, a bag or wherever you're organizing your parts. Sometimes when you're using a harder plastic, you can find the gate location on that part by looking for something that looks like a roughly sanded piece. And usually you're using a closer clip, and you're just kind of doing a very light sanding on this. So gates are you know, most commoditized plastic pieces you'll be able to find from those locations. And it's always interesting to me to see where the flow started for that part, because it does indicate how the other side may look by how the material stitches together, especially the more complex a part gets. Mm-hmm. So my background is working with designs from a practical nature, saying how can this design translate into that end manufacturing process. So what I work on a lot is not just the application, but also is this design good for injection molding, or good for whatever technology that we're really reviewing at that time. I wanted to go over 5 common things that I see when designing for injection molding that are mistakes or things that would definitely need to be at least addressed, acknowledged, or changed in order to get a more repeatable part. The very first thing I'm gonna bring up is draft. So draft is essentially adding an angle to any perpendicular feature of your part. And I'm talking about perpendicular to the mold tool. So for example, a highly drafted part would be a spoon or a cup in a mold, where you have those angled corners going from a smaller cylinder to a larger circle at the very top. This is very, very important from a practical nature, because you need this to release the part successfully from the tool every single time. And because when we talk about injection molding, we're not talking about, you know, 5 to 10 pieces. We're talking about 5 to 10,000 pieces. You want to make sure that you're incorporating draft features to reduce anything that causes either catastrophic failure, you know, pinch and mold, or something that can deteriorate a part over time as you're molding. And by the way, this is the #1 thing I will give feedback on if you do submit your design for injection molding, is usually we are going to catch edges that don't have drafting that require it. At a minimum, we look for 1%. The next thing I want to talk about is keeping an even wall thickness. So when you're CNC machining, you're looking at more is less, where you're removing from a block, and anything that you don't remove is time saved. With other processes, less is more. 3D printing, we talk about the complexity paradox, where you can actually add complexity without necessarily adding cost to this. With draft in mind, with kind of actions in mind about what direction you're pulling your part from, you want to make sure also that you're keeping the wall thicknesses even. This is because of thermal shrinkage. So I'm injecting a very hot plastic that's liquefied at a very high pressure into this tool. When those tools are cooled, and as the part cools down, if you do have something, a wall thickness that is thicker than the rest of the part by a significant degree, it's actually going to have a very, very different rate of shrinkage than the rest of the part. And this can cause bowing, warping, and other unintended effects. One of the things that we see with injection molded parts that have thicker surfaces is something called sink, which almost looks like a thumbprint indentation into your part. And that's literally because there's more stuff there. And in that center of mass, it's still hot, and it's shrinking down. It's basically pulling everything else around it, and it becomes a visible, noticeable entity on your part from the outcome. The way to mitigate that is adding gussets around your boss instead of making a thicker boss to add strength. Adding ribs to your part. So often when you look at an injection molded part, you look in the back and you see this crosshatch of thin walls. That adds strength and stiffness without adding increased thickness to the wall. So always take a look at your wall thickness and make sure that you're staying consistent on your parts. Next thing to add here is what I'm saying, unnecessary undercuts. A really good example, I mean, this is very blatant. I have a hole in the side of my part. How do I use an open shut tool and also make this hole? Well, I have to add a slide to the side, which essentially it would be a cylinder that pokes onto the side of my tool. And when I flow the material around, it'll flow around that cylinder, and then that slide will release outwards before I open my tool, or sometimes during when I open up the tool, and that cavity left over is your hole. Anytime you add this, as Travis mentioned before, it's a cost driver, and this is something that we'll get into a little bit further here. But undercuts can also be mitigated very, very easily. We have a design guide online that goes a little bit deeper into this, but when you are looking at undercuts and other features, there are ways to get the same function while thinking with an AB, a two-part open and shut mold. And often it's creating clever little gaps on the top and bottom of this feature, where you can actually put a slide that makes that overall, when you look at the profile, makes the shape of the part. Again, it's harder to visualize, but easier to see with our design guides here. But just understand that anytime you have an undercut, anytime that you have something that's off center from just a front or rear face of the part, that is something that can be a significant cost driver, and something that may interfere with the with how you can actually tool. It may actually interfere with the manufacturability of the part. And I'm going to talk about this from the application side. The last thing I want to talk about is the second to last thing is choosing the wrong materials for your application. Let me tell you my cheat code with this, which I am extremely guilty of, but man, it works. If I'm designing for an application that is, say, outside, or it's something that you step on every day, or it's a part that is body worn, the first thing I look for when I'm trying to figure out what material I'm going to be designing for is I look at other parts that are in that family or in that environment, and I just check to see what material they are. Is this something in a ruggedized outdoors environment? Maybe I use and it's going to take a beating. Maybe I use a 30% glass fill nylon. Is this part going to go hot, cold temperatures? I may use a different material. But you want to think about your application. And the biggest reason why is we are going to be designing and quoting this tool around that material that you're choosing. And once you press go and you commit to that tool, it's very, very hard to change a family of materials because we are compensating for the shrink rate of the part. We're compensating for certain deflections that may be happening in the part within the tool design. So going from a very stiff, well-behaving plastic like an ABS to something that's a little bit more mischievous like polypropylene may require a brand new tool to do. And it's just something to understand up front. A little bit of research, a little bit of identification on what you need will go a very, very long way as we talk about production of parts. The last thing that I want to talk about is just radii. This is probably my most common theme when it comes to design for manufacturing in general. And whenever you have a specific vertice, a right angle or angle corner, you're adding a stress point. By putting radii onto this point, onto this part, especially with injection mold, you mitigate a few things. One, when we talk, go back to the draft argument here, you're making it a little bit easier to release. You're making it a little bit easier to manufacture. Two, you're mitigating things can happen when you're talking about these acute angles, these vertices where there may be a fill issue or maybe an unpredictable result due to sink, due to uneven wall thicknesses, due to things that internal corner can cause issue with. And so I just recommend where you can, again, thinking about how you're designing and what direction that tool is going to be pulling from, adding radii to the maximum extent. It's going to give you the best results and most repeatable results over thousands of units. It also looks great. All right, and Travis, so where does rubber meet the road here? So let's talk about cost drivers.
So just a reminder to everybody on the webinar to write down your questions, and then you'll have a chance to chat them in, okay? So a lot of times I get questions from our customers. You know, Travis, how can I drive costs down? How can I make my part, time to market faster? How can I make the tool cheaper? So I actually made a list of the very common questions all of our customers ask at some point. So I'm going to go over one material selection. So to the right, that is the materials we currently offer. We are currently working on other materials, but this is what we offer at this point. And then, so going back to the material side, where will this part live? I don't know your design. I don't know your intent. So that's something you really need to look at. Is this part going to live outside next to an oven, or is it going to live indoors under a desk? Those are things you need to look at. And you can actually choose the material for that by looking at the material properties. Now, I found two websites, matweb.com, matweb.com, and Nexeo Solutions, Nexeo Solutions, two wonderful websites that you can go to, and you can actually pick, let's say your part does live outside, so you need some type of UV stabilizer in it. You can actually poke that in first, and it'll give you recommendations. Wonderful websites, I use them all the time, just great, and they're free. And then another thing you need to look at is price per pound, okay? You may not know, but you can actually find out through Nexeo Solutions what the material costs. But there's a lot of difference in the price per pound for material. Give you an instance, high density polyethylene, HDPE, the third line down on the right. The stuff goes for like, $1.50 a pound. And then you got polysulfone, which the stuff is like $12, $15 a pound. There's a whole lot of difference. Okay, then you need to look at also, like I said, the material. What is it used for? Where will it live? And then the pricing too, because the price per pound does dictate the overall cost of the part. The next big driver my customers ask a lot is, how do I shave time off, the part cost? Well, cycle time, right? That's saying time is money. It's absolutely true. So if you look at material cooling time, once again, HDPE versus polysulfone, the cooling time is much different between the two. HDPE is more of a, commodity plastics, cools very fast. Polysulfone, you got to heat the mold. It's almost considered a thermoset. You have stuff like mold cooling, right? So just a word of warning, be sure if you have a mold built by us or outside, make sure it has water circuits in it, okay? It does change the cycle time of the part. It does change the appearance of your part. Mold cooling, essential. Even the mold build can dictate cycle times. Using quality materials. Aluminum versus steel. Aluminum, it's easier to machine. It's very fast cycle times, but on the flip side, you know, if you have really complex geometry, the aluminum can get damaged. Even going as far as using mold max materials, you know, can pull the heat out of the part very quick and it can shorten your cycle time. And then once again, the quicker the cycle, the less overhead the part per part.
This is also something that comes in too when you talk about what production level you want, right, Travis?
Sure.
So if I have a order quantity, say I want, you know, 50,000 a year, then I should be expecting 1,000 parts a week.
Sure.
Once I'm into production. So when we talk about cycle time and when you start saying I want more than X, you have to think about different ways of managing, whether it's, you know, family molds
Sure.
or other ways of designing this. But it is really important not only for your initial order, but to kind of know what the future of this order is.
Sure.
Because it does help us make a better decision on what tool you will choose.
Absolutely. And then another cost driver is surface finish. To the right, again, this is what Xometry offers in terms of surface finish. We do offer some others on a case-to-case basis, but you can always send that in your request for quote. And then just like the surface finish, understanding your part. A lot of times I get quotes from customers, they require let's say an A-class finish. Then after talking with the customer, I realized, you know, you really don't need that. And instead of spending thousands of dollars sending this thing out to get polished, you know, you can just do a D1 finish. It doesn't really matter for their part after all. And then, like I said, the SPI finish chart, those are the Society of Plastics Industry standard. And then, once again, the higher the luster, the higher the price, because it's more labor hours involved to make something shiny than it is to make something dull.
And yeah, and for those of you guys who are actually used to the Xometry website and using our online quoting for things like CNC, you've absolutely seen this. If you've gone from our standard 125 surface finish up to 63 or 16, you see a huge drive in price. And that's because we're slowing down, we're doing different processes to get that surface finish than just milling.
Sure.
And it does add a ton of time. And this is adding time and cost to that fixed cost, your injection upfront, or your upfront injection mold tool cost.
Absolutely. And then another cost driver is post-molding operations. Anytime a hand touches the part after it's molded, it just costs more. There's more labor involved, and the price goes up per part. Sometimes I see stuff like, you know, the customer might want machining done afterwards. Well, you know, by adding a slide or something inside the part geometry, it can change that, okay? Stuff like cooling fixtures, as you see a very elaborate one on the right here, sometimes it just takes a longer cycle time or a better choice of materials, and then you don't have to put that in a cooling fixture after all. Another big one is packaging. I had a customer once that said they wanted all the parts in egg crates, and come to find out after a conversation, we can throw everything in a Gaylord. Okay, there's a big price difference between that. Special handling, that sort of covers the bottom there. Special inspection. Do you really need every part inspected, or can it be a lot, one out of a lot? And then also testing of the parts. Do we need our partner network to do the testing, or can you do the testing once you receive the parts? So anyways, that's sort of a summary of just the big cost drivers in injection molding.
Yeah, and it's just really important also to know where that cost drives in. So, you know, when we're looking at some of those things that change the surface of the part, or for example, what type of metal we're choosing, that's going to be on the actual tool itself. That gives you that higher upfront tool cost. But post operations are, you know, manual touches of that part, and that's going to give you a higher per part cost. So sometimes it does make sense to rethink, all right, so at some point we're doing this manual action over and over and over again. If I pay this much more for this action to be done within the tool, I may actually save money over X amount of parts.
Sure.
So we're here to help you figure out those break evens as you're looking into these options. So how do you guys get started though with Xometry's injection molding service? This is a service that's been recently added to our site, and it was actually really exciting because we joked about a soft rollout, and then we got a flood of customers coming in, and then we started marketing for it. So it's really exciting to see this need for injection molding from our Xometry customers. Right now, it is a form. It's separate from our instant quoting site. So if you do go to Xometry.com, you click on our capabilities page, you're going to see a drop down for injection molding. There are a couple links for get a quote for injection molding, and this is where you write your love letter to Travis.
Yeah, so I will receive it.
So at this point, you will upload your 3D CAD model, which is the minimum that we need for any service that we offer here at Xometry. Is a 3D CAD model. You can also upload your prints, so we can actually see what's critical for your part and its function. And then from there, very standard, selecting your material, your color, your finish, if there's a fill required, and some other options. One of the things to note right now is that we are looking at sub 10,000 units or below right now for our initial launch, and we're expanding from there. And if you are looking at quantities that are between like 1 and 250 units, I may come back and ask you a couple questions because we have some options with 3D printing and with urethane casting, maybe a better option for that. Really, a sweet spot for injection mold, I actually think starts at 500, but really 250 is probably a good start point on the minimum quantity to get the bang for your buck when you're actually doing injection mold services. And that's because you have that initial upfront tool cost. So the parts may be cheap, but you're still paying for that tool there. So we have a lot of options here. We want to be your one-stop shop for manufacturing on demand. So it is. So I will ask you a question if you're asking for 12. Now I also understand sometimes you just need that part. You need that part in that real material, and it does help us speed up the quote if you do put in the notes that I need those parts. I need 12 of them. I need them injection molded. I talked about our other services that we offer. So Xometry, we are constantly adding new technologies, new materials to our lineup, and a lot of this is taken care of with our instant online pricing and lead time system, where you can not only click price and order your parts for say CNC machining or sheet metal, but we also do the whole supply chain management of that. So we have an entire manufacturing partner network, and we're able to pair the specifications of your part with a partner that's best able to build that all across the United States. So it's a really, really powerful way to build and manufacture your parts. And it all starts via our website, Xometry.com, for that information. So I think at this time, I got a little ahead of myself here, but I think we're really happy to answer some questions. Oh man, we're right on time.
Right on time.
High five, guys. All right. But we really do want to start answering some questions for you about injection molding. So please, I already see some are listed out here, but feel free to start typing away, and we'll try to get to you. Blair, do you want to? You can MC this.
Yeah. Hi, everybody. Also want to say for anyone that joined late, the webinar was full. We apologize for that. Demand was really high for this, which is really exciting for us. If you were unable to join or had to join halfway through, we're going to be sending the recording out to everybody. So please just stay tuned. And if demand is there, we're going to have another one of these sessions as well. But to go to the Q&A section. So we had a great question from Barbara about silicone versus food grade plastic. So is silicone less expensive than food grade plastic?
Food grade plastic is much cheaper. That'd be like polypropylene, I guess like polyethylenes. If you could imagine a milk jug, okay, it has to be obviously FDA compliant to hold milk you're pouring into your cereal. Very cheap material. It's commodity plastic.
Okay, great. Thank you, Travis. Keep these questions coming. So we have another one. This is actually for you, Travis, but it says, Greg mentioned a couple of websites to use as resources for material selection. Can you list them again, please?
Absolutely. So one of them is MatWeb, MATWEB, all one word, .com, and Nexeo Solutions, NEXEO Solutions.com. Wonderful websites. I use them every day. I'm not even giving them a plug. It's true.
I'll be honest with you too. When it comes to material properties for CNC milled components as well, MatWeb is a fantastic resource. It's like the Wikipedia of material properties. It's very, very good.
Absolutely.
We had just an admin question here. Will we be sending the slides as well? Yes, we can send the presentation to you as well as the recording. Another question here. How can you determine and make sure how many ejector pins you will need in order for the part to eject properly? That's from Jessica.
Well, okay, so it's a loaded question. Just looking at the part geometry, if you can imagine anywhere it's going to stick inside of the tool, you will need some type of ejection. There's many ways to eject a mold. You got ejector pins, you got ejector sleeves, you got stripper plates. There's so many things you can do to a part to get it off your mold. But once again, it's sort of, it depends on the part geometry, yeah, and how big it is, right?
So, and I'll kind of rewind back to this piece here. So this piece that I have on this slide, it's a flexible material, which means that can kind of snag in place. If you grab this, it'll feel like a kind of like an elongated eraser as far as the texture goes. This has a lot of ejector pins to this, and this is essentially because you have all these protrusions around these features here, and they can all be potential snag points. So by giving an even push to get this part out, you mitigate the risk in a production environment. So that is a, you know, and that also comes down to as well, like how many are you looking to make, and what type of tool we're making for this job. So it comes down to making sure that we have the job scoped out correctly in the beginning as well.
All right. We have another great question here. What is the normal lead time of injection molding, and who owns the tooling?
Okay, so the normal lead time, it's anywhere from 2 weeks on. Once again, depending on, you know, the complexity of the part, and then how many pieces you're going to want initially. And then who owns the tool? You, the customer, owns the tool. And the tool is held at our partner network. For whatever reason, and hopefully never, if you need to move this tool, it can be transferred anywhere. It's a standard DME style or mud style unit tool that can be brought anywhere in the United States or even overseas to run your mold.
And just something, you know, something to note there on lead time. It does depend on the complexity of the parts. And when we talk about, you know, the 2 to 3 week time, if you are building, say you're doing a job for 7,500 pieces, what we would be looking at is getting a first article validation to you. So usually that's 10 shots. So 10 pieces, we'll get that in hand, and you'll be able to review it, say, yep, this is good, and we'll move forward with the rest of the production. Typically, if you have sub 500 pieces, we'll do it all at once, because the opportunity to do that job is just about the same 10 shots to 500 shots. It's just about the same level of effort, so it does make sense. And you know, most of the time, we're pretty good. You know, it's something where you're going to get your parts and start working with them on your project. So we're always happy to talk a little bit more about that, but a lot of this does come down to, you know, we don't know your parts yet. We want to, and we can align and engineer on what's best to get those parts to you, and what level of batches.
Yeah, and to that point, actually, we did have a great question from Frederick here. If they provide part files and your team has some recommendations for either ways to make them less timely or more cost effective, is that a service that we offer?
Yeah.
You offer?
So I'm happy to talk to that. So I want you to have a successful project, and I think everybody here at Xometry, I mean, we feel you. We are a bunch of engineers ourselves. We've cut our hands on a lot of parts, and we want to make sure that what you're working on is a success. So we never want to be in a situation where we say, I told you so later, and we are going to give you suggestions on design for manufacturability. That being said, I do want a CAD file that at least, you know, remotely starts looking like a injection mold. So start with our design guide online, and again, that's under our website, under our capabilities page. You could go to injection molding and click on our design guide, and that's going to help get you some basics to make sure that you're designing right, as well as a bunch of tools in most professional CAD programs to help look for draft analysis and other features that can really help you get the right part out. And once it's in our hands, though, we're always happy to say, you know, these 3 tweaks are going to help a lot. But when we talk about side actions, like I said, you know, you add a side action, and all of a sudden I see $1,500 in my head. So it's very easy for you to design that in CAD, and sometimes it's very easy also to mitigate that to reduce the complexity of the tool.
Just to add to what Greg was talking about,
yeah.
I do DFM, design for manufacturing, on every part that comes in through RFQ. I run it through SolidWorks thickness, and I also do a draft analysis on it. And then I also run it through SolidWorks plastics. It's the equivalent of mold flow. Mm-hmm. Gives me cycle times, part volume, weights, those types of things. If I see something just crazy, I'll no quote it, and I'll get back to you and I'll tell you why. If I see some minor changes that need to be made, I will quote it, and I will give you design feedback.
Quick question here from Jess. We mentioned CAD files. Is a .stl valid?
I'm going to say negative on the STL file. So we professional CAD output would be a parasolid file like a XTXB, a solid part file, step file. These are files that can actually be translated into a solid model space. STL files are a little bit different in the fact that they're a series of triangles. So for example, there are no circles or no cylinders in STLs. There are only a series of flat planes. And so it's something that we can't program a machine against. And obviously, like injection molding is a byproduct of a machining effort. So we can't use that for any injection molding. It would have to be, I think a big universal file is step, where most professional CAD pros can export in that model.
Mm-hmm. Perfect. Yes. We have quite a few questions here. So if we
awesome.
don't get to you, our apologies. We'll reach out to you separately, specifically if it's a part-by-part basis.
Mm-hmm.
But here's a question from Adam here. What is the maximum size that injection molding can handle? As I have a part that's either way. We'll make it very general, Adam. What is the maximum size injection?
Both of us are grinning here. I mean, car bumpers are injection molding, to be fair.
Yeah.
But let's talk about what Xometry, what we're looking at right now for our scope of work, and this really also narrows down to that we want that specific surface finish in sub 10,000 units. So Travis.
Yeah. So you're right. I came from a place that molded garbage cans before. So, but in terms of geometry, we like to stay in our wheelhouse about 10 by 10 by 10. That's about what we're shooting for. Of course, there's exceptions. We've quoted some panels before that were bigger, and then
Yeah. So we are on purpose limiting the scope of our work, but something to note that is that we are working with manufacturing partners that are actually channeled within Xometry's manufacturing network. And these guys are professional shops. Some have been around for 30, 50 years doing injection molds, so they know their stuff, and they're working on very high level production. So we're doing this on purpose as we're building up our website around injection molding, our service there.
Okay, another question here. So for mold-in inserts, such as threaded fasteners, is it cheaper to do them during molding or a press-in insert after molding? Do we offer these?
Okay, so yes, we do offer them on a case-by-case basis. Depending on the volume of your parts, if you only need 100 parts, you might want to look at just heat staking your parts in post-molding. If you're looking at 10,000 parts, you probably want to insert these things while molding.
Okay, perfect. Another great question, I think, from Ian. Can you use two different? Oh.
Okay, so you're talking about like something like overmold. So can you shoot two different materials within a tool?
Two-shot.
Yeah.
Overmolding.
Yeah.
Yeah. Yes, you can, but unfortunately, Xometry, we don't offer that at this point.
Yeah.
But yes, you can. It is a very valid process.
By the way, because I geek out on this stuff, if you go look at videos of how that's done, it's really neat sometimes where the tools actually articulate and will do its first shot, and then essentially the tool will lean back and the parts move back, and then do a second shot with the secondary material. It's really, really interesting, but you're also talking a very different style production than what we're currently offering.
Yeah, so the word of warning is with two-shot, very expensive tools. I mean, you're literally buying two different molds because you're molding the substrate and then you're molding the overmold. Okay, so buyer beware.
All right, so we have a great question from Michael here. Are there various options regarding the material for the injection molding tooling? such as maybe a mold that does not need to be used for a long run or large quantities? Basically, are there cost reducing options available for the actual material for the tooling?
So this is talking about bridge tooling.
Okay.
Yeah, so I think that's a good question.
Yeah, so a lot of times from our customers, they don't need the million components this year. They need 10,000 to run their pilot program. So that's great for Xometry, and that's where our fit is. We will help them with that bridge tooling. We'll help them get started, and then get those 10,000 pieces to them, and then maybe next year they're ready to run a production mold, and then they go out to their partner, and they'll run the million parts. But that's where Xometry fits in. Is that even that bridge type tooling, prototyping, low volume, low cost.
Great question from Oleg here. Are you doing injection molding in the United States or China?
We are. All of our we are in the United States.
CONUS.
Let me check. CONUS.
Yeah.
All of our partner network is in the United States, and then everything is tooled stateside, molded stateside.
Great questions. So a few more here. Some of these are specific, and as I mentioned, we'll get to those individually. One question is, will you take on a new material for a project that you don't have listed?
We do quite a bit. Our customers in the RFQ, there's a spot in there that says customer supplied. We do run customer supplied material. Of course, it needs to fit within our wheelhouse. It can't be like some special titanium glass filled whatever. It needs to be some type of standard materials. But yeah, we are absolutely open to that.
Great. So we have two questions about draft here. So one question is, what do I base draft on if the flat side of the part has multiple planes?
Ooh, so this is actually, I'll try to tackle this first, and then Travis will slap me on the back of the head and tell me how wrong I am here.
No, man.
But when you are talking about a part with multiple planes, we're going to be looking at first off, an A side and B side. So what is the primary plane for this part? And it's usually, a lot of cases when you're designing, it's the front plane, and it's something that we could look at, and that's where you're going to do your analysis based off of there. Just keep in mind anything that is considered kind of an undercut or an invisible surface. If I'm looking at that plane, so like if anything that's under that shadow or perpendicular to that, may require some sort of secondary operation. So when you are working on parts that are multiple planes, you sometimes want to fib it. You sometimes want to say, you know what, this thing's off, but I'm going to make on this side a little bit more contoured so I could see it on that plane and I could get that molded. Just keep in mind, you do want to keep the even wall thicknesses. But you can mold a lot of different parts. It's just really important to note that every time you have to push, a different type of tool in to kind of, plug that hole or hold that gap, you are adding money to that tool. And so typically we see, tooling costs, $3,500 to $9,000 or something like that. But by adding something that has multiple junctions, all of a sudden you're getting in that $10,000 to $20,000 to $30,000 cost, and it's because of these extra actions. So a little bit of design intent up front can save you a lot of money.
Yeah, that's a great definition. So another thing to look at too is all CAD programs, which you're designing in, CATIA, Pro-E, SolidWorks, AutoCAD, any of them, all of them have a draft analysis tool. So if you can imagine your part and where the parting line would be, if you go off that plane there and you just run your draft analysis, you can bring it down to, let's say, 1/2 degree and shoot the arrows, front or back. That'll tell you exactly, where the draft needs to be. The part has to come out of the mold. If you can imagine, if you have 0 draft in there and the part goes to eject, you're going to get scrapes all down the side of your part as it ejects.
All right, another great question here about our partner network. So from Shauna, since you all have a partner network that assists you, how do you manage the customer's intellectual property?
Oh, that's a great question. And this is something that, again, our manufacturing partner network is for all the processes we offer here at Xometry, as well as we do have internal capacity for manufacturing as well in certain fields. So your part, the identification of you, the part's function, and any type of company information is actually scrubbed when it goes out to the partner network. So we are working on specifically a unique internal part ID, redacted drawings, and giving our partner enough information to make that part successfully. Something to note is that these are manufacturing partners. This is not a brokerage. We have these manufacturers sign up, and they are vetted through the Xometry network. So we are working to get them onboarded, and we are working with every single one of them under an NDA through Xometry. So the NDA chain does exist. One thing I do want to note is we do work with a lot of defense, government, and military work, and that has something called ITAR, and some of these and there's other export like EAR, like export controls. If that does come up, it's something that we want to make sure it's identified, and we have places on our website to identify that work, because that does position how we channel work through our manufacturing partners. And again, by digitally controlling this, by working this through Xometry's chain, they're going through a Xometry site to manage and track work, send updates. We are keeping very, very tight control of intellectual property.
All right, we're going to do one more question here from Alexandru. Can the mold be pushed out by air instead of using those pins?
It can. There's a thing called an air poppet. A lot of, if you can imagine a cup, they have an air poppet on the core. So once it's molded, mold opens up, air releases the air poppet. It's like a little check valve, and it basically pushes the part off, or it breaks it loose at least. And yes, it can be done. Like I said, once again, depending on the part geometry, there's just a lot of factors in getting a part off the mold.
But typically, again, for the scope of work we're doing, we're probably going to be using ejector pins for everything we have.
All right, actually one more, sorry, from Michael. Over what thickness of any section of the part does injection molding not make sense?
Let's see, very thin walls, sub 30 thousandths, the plastic basically freezes off. It won't push through. Once again, depending on what type of material as well, but I'm thinking like a commodity plastics like polypropylene. It just has a real hard time squeezing through. It's just something very long and linear. And then Greg also talked about the thick sections in a part. Anything over 3/8 of an inch. Once again, depending on the type of material, I'm thinking polypropylene, you can get sink marks, longer cycle time. Again, these are all cost drivers.
And just when considering sink, so when we're talking about a thickness differential, sometimes you just need mass there, and if you are okay or accepting of sink, which will be an unpredictable cosmetic, we consider a defect. But if it's something that we talk about, it may be, and it's okay with you, that's something that at least we can engineer around or talk through. But when we do identify this, so if this does go getting ready for production, again, we want your project to be a success. So if we see something where we know there's going to be through simulation a defect or sink or something that matter, we're going to point it out, and we're going to raise a few flags around it, because we really, really want to make sure that that's what you're intending in your project.
Sure.
Yeah.
Sorry to do this to you guys. We have one more question. I think it's good. So what is the largest volume and smallest thickness you've done with titanium?
Oh, well, this is so this is, yeah, we're talking that's something different there. So that would be more on our other side, where it's machining, or even like if we're doing a custom quote for direct metal laser sintering. That's where I'll leave that. But it's a different process than what we do with injection molding, where injection molding we're focusing on polymers, thermoplastics right now.
Okay, perfect. Well, thank you guys so much, and thank you again to everyone for joining us today. We hope you found the presentation to be helpful, informative, and valuable. We'll send around the recording and the slides. So we actually did have a question from Boyd. Thank you. I'm not ignoring you. We will send us the slides, as well as we'll make sure to include those websites that Travis mentioned, because I had a few questions on those. We're always happy to follow up online. If you have additional feedback or questions, please always reach out to our team via chat or by emailing support@xometry.com. As always, we want to be your one-stop for manufacturing on demand, and we're looking forward to seeing lots of injection molding quotes orders, all that fun stuff. But we really appreciate all the feedback here. And if anyone joined late, as I mentioned, we're going to be sending around all this information to you all shortly. So thank you again for joining, and have a great rest of your day.
Guys, yeah, and again, thank you so much from Travis and myself. We love talking this. We love making great parts for you. And just talking about the interest in injection molding here, I mean, we did have a full house today on this webinar, which is just something really, champagne problems, but really exciting to see the interest. So just keep it coming. Thank you so much.